Hi guys, my name is Chris Jackson and I'll be going over my final results for this class's project. And my topic was thermal fatigue analysis of a brake rotor in racing applications. So just a brief overview of my project. The goal of this was to analyze fatigue within a brake rotor as a result of thermal saturation experienced within racing scenarios. So, within racing applications, these rotors go through constant heating and cooling, and I wanted to see how material properties affected these results or the performance of the rotor. So any parameters that I used were based off of measured and calculated data from my own karting experience as well as Formula SA experience here on campus. So dimensions of the rotors, they were based off nominal values existing within practice. And material properties, they were all used within the SolidWorks and the Workbench database. So here you can see an overview of my model. I basically sketched this. I have my overview of the sketch on the bottom right, and I went ahead and extruded that. And if you guys want, you can see the Progress Report 2 video where I went ahead and made this model. And when that was complete, I imported it in the Workbench, and I can select my materials here. And you can see on the top left, these are the materials that I used. So I used an aluminum alloy, hardened steel, and a structural steel, and the properties are listed right here. And actually, for my hardened steel, I used Boeing as a source where I could put in my alternating stress as well as cycles to further customize my solution and look at different possible capabilities here. And I mentioned that SolidWorks has a material database, and you can see that here as well. And so further iterative studies that I want to run, if I want to compare any more materials in the future, I just go to SolidWorks or any kind of database that it provides these properties, and I can further import them into Workbench if it's not existing there already. So here is the mesh of the model. When I went ahead and imported it, I went ahead and generated it as fine mesh, and I wanted to do this to increase the accuracy of my results. And there's not really any variation of the mesh except for along the edges, and it's more concentrated there. And here are the boundary conditions and constants of the simulation. So the geometry of the rotor and the thermal characteristics as well as the static structural characteristics, they all remain constant as well as the time element. And here you can see that the moment was applied as well as force in the y and the negative y direction, and this is representative of pad force applied to the rotor that it's experiencing. It was fixed on the tabs, the 6 tabs, so here, 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 and here as well. And this is basically where the rotor bolts onto the hub assembly. Now looking at steady state thermal, there's heat flux, convection, and radiation, and that was all applied to the model as well. And this is just a general overview of the model tree within Workbench. This is an overview of the simulation. So I've mentioned 2 different states now, and that's a steady state thermal and a static structural state. And basically how this works is steady state thermal will go ahead and run its results in a solution based off engineering data and geometry that I imported, and then it will pass its solution on to the static structural, and this will run and it will consider this within its results. So it's all encompassing. It pretty much considers both thermal aspects as well as structural aspects. This is some of the plots that I generated for my results, and there's not a whole lot of variation here. They're all pretty much the same. What I really wanted to focus on here was fatigue, and you'll see that later on. Total heat flux here, again, not a lot of variation. It all pretty much remains the same, but I wanted to use this as a comparative study, just like we had used within lab. This is my plots of total deformation, and here we can start seeing some variation. I knew, by nature, aluminum was a softer material, but I just wanted to include it just for comparative purposes. Equivalent stresses, again, I chose to include this as well. There is variation, and you can see that in some of these plots. Same thing with equivalent elastic strain. And here's where I really wanted to focus on, and this is the different plots of the life of the rotors. And the top left, I left as my baseline is the structural steel, and then I went ahead and looked at any kind of variation within that plot. So it's pretty much concentrated where the tabs are, where it bolts onto the hub. And I went ahead and used that as a hardened steel just to look at the effects of that to improve the performance of the rotor. And then from there, I went ahead and looked at the effect of just hardening the entire rotor, and that's, you can see that on the bottom left. And then on the bottom right is the aluminum alloy. And same thing again with the plots for damage of the rotor. And I think among all of my results, and I'm going to discuss this here in a second, I really think that the way to go is the steel rotor with a hardened inner lip, even though that the hardened steel has the better plots as far as factor of safety. So concluding this, I was able to examine the different effects of material properties within, an interest of mine, and see really how that affects fatigue as well as plots of stress, strain, deformation, and thermal distribution. And upon consideration and of all this, I feel that the structural steel rotor with a hardened inner lip proved to be the best option, and that's at the top right, as you can see here and here. And I chose to do so even though this hardened steel was ultimately the better performing rotor, just for economical factors and like in a business sense of mind. If you were to go ahead and manufacture this or make this for a business, it supports all the criteria that you would need within racing applications. It's a safe rotor. It distributes thermal stress and everything and temperature evenly, and it's well within the lifespan that you would need for a rotor within this application. So I thought that it was a good consideration in this. And, looking into the future, I can analyze different materials such as composites or even things such as like in a titanium rotor and really see what this has within the same type of study. And, run all the same baselines and everything like that and same constants and boundary conditions. And, it would be easy. So I really appreciate you guys listening to me and taking the time to watch my presentation. Please feel free to look at my final tutorial as well. And if you have any questions, please feel free to reach out with me. Thank you.